Right, stars. Okay, we hopefully you know the basics for the stars. That stars start to form because you've got gravity pulling in all particles of dust and of gas. And an early star is a protostar, okay? And that's where the gravity's pushing in together. As it gets all the stuff together and the volume decreases, your gas laws, that's going to make the temperature increase, the pressure increase. Okay, and then eventually you're going to have enough pressure to produce forces that are going to counteract that gravity, and that's when we have a main sequence star. Now, the main sequence is by far the longest part of a star's life. Now, you get small stars, they tend to have a longer main sequence than big stars because big stars are using up all of their hydrogen quicker. But still, for both sorts of stars, main sequence is the longest. Then what happens then when they start to run out of hydrogen is, well, what happens is they start to be able to fuse some of the helium together. This causes the star to, some of the outer layers to expand, and we get a red giant. After the red giant, what's happening then is when everything's sort of run out and you've got some of the other atoms fusing, we've then got a white dwarf. Now, a white dwarf is when you can also have some planetary nebula given off, which are when the outer layers are sort of released and they can go off. Planetary nebula could form planets somewhere else, but that's what's happening. Now, we've got this Chandrasekhar limit to think about and what that's all about. Now, for the white dwarf to be able to be stable, what happens is that we've got the electron degeneracy pressure keeping it stable. Now, luckily, you don't need to know too much about what that means, but basically it's to do with electrons being squished into a tiny, tiny, tiny place. And because you're sure where they are, you can use the Heisenberg principle, which isn't in the A-level course, and there's a massive, massive gain in momentum. Now, because of that massive gain in momentum, there's a large pressure. That's what supports white dwarf stars. So to support them, you've got some gravitational forces pulling in, but you've got that electron degeneracy pressure pushing out. And that's why you can have this as a white dwarf. Now, what happens is the white dwarf over time will just cool down. It's a dead star. It will cool down eventually to a black dwarf. So it will cool down and you won't have as many photons being emitted. But that electron degeneracy pressure is the thing that keeps it stable, that stops it going supernova, which we will look at down here. Now, the limit, the size that the star's got to be, that it can be a white dwarf, that's the one that's called the Chandrasekhar limit. And if you've got a star that is, the maximum it can be is 1.4 times the mass of our sun. So anything less than 1.4 times the mass of our sun, end of the life is going to be a white dwarf, okay? Because this electron degeneracy pressure is going to be able to keep it as a white dwarf. Now, that won't happen with bigger stars. With bigger stars, they are going to form a red supergiant or a super red giant. I looked it up, I can say it either way. So we've got the red supergiant, similar thing to the red giant, we've got some other fusion happening, and because the other fusion's happening, we've got an expansion to it. But then what happens is it goes supernova. And the reason why it goes supernova is because this electron degeneracy pressure cannot balance the gravitational forces, so it collapses in on itself. As it collapses in on itself, the outer layers sort of bounce off and cause an absolutely massive explosion. Okay, so absolutely massive explosion. What we're going to be, it's going to shed loads of stuff out into the universe, and that's what makes up, like, everything. Everything heavier than iron has got to be formed in a supernova. Here you don't get a lot of stuff scattered across the universe. Here you do. So most stuff is made, most atoms are made by supernova, and every single atom heavier than iron must be made that way, because if you remember when we did nuclear fusion, iron's the most stable. You don't get any energy from fusing iron. You'd lose energy. So after the supernova, you can get a neutron star. Now they are called neutron stars because what happens is electrons sort of combine, get squished into protons, and that forms neutrons and some neutrinos and antimatter as well. But so we've got the neutron stars caused by that happening. Now that happens for stars that are bigger than 1.4, but less big than 3 times our sun. So you get a neutron star happening for those ones. The other one is you get a black hole, and a black hole happens when it's 3 times the mass of our sun or more. So all you need to know about the Chandrasekhar limit is that it tells you whether you're going to get a white dwarf or whether you're going to get a supernova, and it's about 1.4. Okay, some sources said 1.3, but most of them say 1.4. What you need to know about the electron degeneracy pressure is that it's what keeps a white dwarf stable. And if you can't have that, supernova. Okay, leave me more messages. I'll do some more videos later.